You might have seen my previous video on fluids. It was not very serious, but I want to make an addendum to that video and explain a bit more in detail the mathematics behind the fluid situation. So let's start with some motivation why we care. Well, the last major update, Factorio 2.0, we got a new fluid mechanic. A lot of problems with throughput was solved in 2.0. Now the situation is that the fluid in the same system, they have infinite throughput, meaning that if you have two pipes that are connected, they would always instantly have the same level of fluid instead of things flowing through a pipe all the way down. A limit to this system is that your your system can only be at most 320 tiles. If it's longer than that, you'll see this liquid symbol, meaning your liquid is too long and the whole system doesn't work. And in that case, you need a pump to separate the system. You need a pump to separate this one system into two systems, one on the left and one on the right, and each of those would then have less than 320, and that would fix it. Okay? So you have to use a pump for big fluid systems. Now let's talk about the problem that might show up with this new mechanic of throughput. Okay? First, here are some examples of what I mean when I say systems, fluid systems. I can say that if I have a pump between two pipes, they can be considered as two separate systems separated by the pump. And if I have an assembler connected to some outside pipes, these two are considered as two separate systems. Okay, so the internal fluid storage of a machine is considered separate to the outside system. And well, unless you have two machines that, okay, for something like a Fedora machine, you might have the sockets being bidirectional. And if you connect the two machines with matched sockets, their internal storage system is considered as a single system. Okay, just like two pipes connecting. And the problem is that there are throughput constraints when fluid travel between two systems. Okay, even though you have infinite throughput in the same system, when it comes to two separate systems, there are still flow constraints. Okay, the setup is that a pump can have a throughput of 1,200 per second, or if you use legendary, you have 3,000 per second. And if you don't use a pump, if you just have direct connection between a system and a machine, this socket has a throughput of 6,000 per second. Now, how is this computed? It's computed using a system called pressure. You might have not even noticed that there's pressure in this game because of this new system in 2.0. So the thing is, if I have a tank that's nearly empty, or the output tank of this pump is nearly full, then this pump cannot pump at 12,000 per second. It would pump at a lower ratio, and that's due to the pressure. Okay? Now here's the precise formula for how to calculate using pressure. And the initial assumption is that the maximal speed of the throughput between two systems is 100 per tick. That's 6,000 per second. Therefore, why you saw the number 6,000 earlier. 100 per tick per socket. Okay? If your machine has two sockets and you input through both sockets, you get 200. Okay? But the true flow is almost always lower because of the pressure. Okay? The true flow per tick, here's the formula, is this base 100 times the pressure ratio of the source times the pressure ratio of the target. And the pressure ratio for the source is computed as the level, the fluid level. So if your source is 50% full, then the pressure is 50%. Okay, and the target is computed as the inverse level. Okay, so if say your target is 80% full, then the pressure is 0.2. Okay, that means if your target is too full, the pressure would be very low, and therefore you cannot pump a lot of fluid through it. Now, if you use a pump can only send 1,200 at most, right? So whatever you compute here is further capped, is further truncated at 20 per tick. That's why you almost never notice there's even pressure in the stream because most of the time it gets truncated. When you do notice, you would notice this if this number is below 20, right? That means if this is less than 0.2 or this is less than 0.2, you would notice that your pump is not pumping at top speed. Okay, so why does this matter? Why do we care? So let's think of a few situations. Suppose you deliver a volume of fluid, a volume has 50,000 capacity, to a station, and the station has 2 tanks as buffers, which is also 50k. You would have your volume delivering the fluid, pumping the fluid into the tank. Okay, so say you have 3 pumps sending the fluid, unloading the volume. Okay? And you would expect a throughput of 3,600 per second. Suppose the buffer of the 2 tanks now has unloaded 40,000. The volume has 10,000 left. Now the pressure is dependent on the target, 40,000. It's 80% full, so the pressure is lower than or equal to 0.2. This would cause a low pressure and a low pump throughput. And so the real throughput at this last 10k of these pumps would be much lower than 3,600. So it in fact takes longer than expected for the train to unload, which could cause a train jam if you have set up your train system to be sensitive to these problems. Okay, now another scenario, the opposite scenario. If you deliver 50,000 fluid to a station which has, say, 20 tanks, 20 liquid tanks, that's 500,000 capacity. You unload the whole wagon, and now your tanks are 10% full. Suppose now you have a factory that uses the liquid from this tank, but because the level of the tank is so low, it's only 10%, they cannot push liquid to the machines quickly enough, right? Because you have a low pressure, the throughput from your tank to your machines would be too low, no matter if you use a pump or not, right? And now it would be possible that your machines are just straight up short on their ingredients because you're not pumping them in fast enough. It's similar to the idea of even though you might have enough material on your belt, you don't have a fast enough inserter to insert them, right? Even though you do have enough fluid in your tank, you don't have enough pressure to pump them into the machine. And this could cause a lower output than expected from your factory. Okay? So that might be one of the reasons why you see a lower SPM than you initially calculate, especially in a high throughput factory like when you use all the quality stuff. Right? Solution to the pressure problem is barrels. It's not my solution, it's many people's solution. Let's introduce barrels. The benefits are clear. With barrels, you can reduce the amount of pipes in your system or reduce the distance of your system, therefore reduce the need of pumps. And there would be less concerns about pressure. And with no concerns about pressure, you have a fixed rate of flow. Right? Each barrel can contain 50 fluid. And you might get even higher throughput because a green belt of barrel can send 12,000 per second fluid compared to a legendary pumps which can only send 3,000 per second. The downside is, of course, you have to make a bunch of barrels. You have to load and unload, whereas you could have just put 4 legendary pumps here, but I also consider that as very ugly. Now the standard setup for barrels is you have an you have a loading factory that loads liquid into barrels, and you put them on your belt, send them to something far away, an unloading factory that unloads the liquid and use them, and then you send the empty barrel back through a return belt. So now you can barrel your liquid in a centralized location and distribute them in different smaller factories, then return the barrels to the original station. Well, if you look at this picture, it has a really low throughput, right? There's lots of gaps, lots of empty spaces, and in this case, you might as well just use a pump. Let's look at a better scenario. Say when you are making a metabase, you might see this. Now you have a factory that can make 240 barrels per second, and you send them through a green belt to a different factory that consumes a lot of barrels and send them back. And if you continue this would just be a perfect loop that goes forever. It never gets stuck. It just goes on. But this would be a really ideal situation. It's too nice to be true in practice. Here I only have one machine. I have a loader that unloads the output into both sides of the belt, and I only have one machine that's unloading, and it's a perfect loop. It's a really nice looking loop, but in practice you're gonna have more machines, and you're probably unloading with inserters instead of loaders. So here comes the problem. It's called the barrel flux, named by Bigfoot, not by me. The barrel flux is the amount of barrels on the return belt, okay? By definition. So it's given by the amount of barrels up here. It's to be considered as a collection of barrels that are not used. You cannot use them whatsoever. Right? They're on the way back, during which time you might be short on barrels. You might be short on empty barrels. So this could be a concern. While you wait for the empty barrels to return, you would like to provide the barreling station with empty barrels to compensate for this gap, this waiting. Now, if you compensate too much, then the unbarreling station might be jammed because now you have too many empty barrels. So the amount of compensation is usually calculated using the barrel flux. Now, here's another problem. Barrel flux, again, it measures the number of barrels in the return belt, so it depends on the build. It depends on the belt speed and the belt length of the return belt. And updating your factory, say upgrading your factory, would change the barrel flux. Right? If you have shortened your belt, or if you have increased the belt speed, there would be less barrel flux, and therefore you would need less compensation. And whatever compensation you have added to your previous factory would be too much, and you would get stuck. Now, that was the problem that I explained, but what's really happening here? You observe that if an inserter picks up a full barrel down here, then the whole chain, this whole belt of barrel would move to the right, and you get an empty spot here on the left, which you can consider as this, I propose the notion of the anti-barrel, this empty barrel, this empty spot on the belt. I call it an anti-barrel. And this anti-barrel should have been fixed by an additional barrel coming from the barreling station, but that barreling station might be waiting for this barrel, this empty barrel. The empty barrel is put on the right-hand side of this return belt and takes a long time to return to the barreling station. So there's the discrepancy. The empty barrel shows up on the left, but the empty barrel shows up on the right. They are supposed to be dual to each other. They're supposed to be counterparts of each other. But the gap, when you pick it up, it was here, and then everything shifts to the right. The gap instantly teleports to the end of the chain. While the empty barrel cannot instantly teleport, it has to go through this slow belt to get to the left. And this, I believe, is the fundamental reason of the problem caused by the barrel flux. An obvious solution you might see is why not just add a buffer? Put some buffer chests on the left in your barreling station. You can do that, but the problem is that the size of your buffer chest is dependent. I believe it should be equal to the size of your barrel flux. And if you're dealing with barrels, to start with, you probably have belts that are longer than 320. Now 320 is a lot of belts, which gives you a really big amount of barrel flux. And one problem is with barrels is that barrels have a stack size of 10, only 10. So a chest can only hold a very small amount of barrels. Therefore, you would have to build a huge buffer for barrels. So here I propose a different solution, a solution that solves the problem with the empty barrel. My proposal is that you use a looped belt. Okay? It goes on a loop. And why does this work? It's because if you pick up a full barrel now, you get an empty spot, the empty spot, it doesn't get stuck to the end and instantly jump to the left. It gets forwarded up to this spot. And when it reaches up here, it would be pretty much the same time that this unburning machine would output. So this upper inserter would output the empty barrel into the slot of the empty barrel. So now you do have a correspondence between the empty barrels and the empty barrels. I believe this solves the problem with barrel floods. But before I show you an implementation of this, there's an obvious problem. It's that the inserters can only put items on one side of the belt. So this inserter can only put items on the right hand side of the belt, which means your empty barrel better comes from the right hand of the belt. But when this inserter grabs, it could grab something on the far side of the belt. Okay? So your empty barrel might show up on the far side of the belt. And for this system to balance out, you really should only use one side of the belt. But that reduces the throughput of a belt to only 6,000 per second, which is 2 legendary pumps. And now you would ask, is it really still worth it to get a throughput of only 2 pumps? Is it worth all the trouble? Now this can be easily solved using a lot of balancers, using a lot of belt balancers. And here's my build that I propose. I've run this a little bit, and I don't believe this is a perfect build. It works. It works all right. It's the problem with how many compensation barrels is fixed here. So I have a barrel provider here to this last machine, and if there's not enough empty barrels, it just inserts some, and this automatically balances out. It doesn't insert too much, so it never gets stuck, even if you upgrade or downgrade your machines. And there's a lot of balancers. It's really ugly, but if you can do better, please do. And what happens is that you have machines up here. They take empty ones and outputs the full ones into here, and they get merged. And similarly, you take full ones here and output the empty ones, and they merge up here. And this whole thing is a loop. So when you go up here, it loops down, and which satisfies what we've been discussing, right? You have a loop. You have a genuine belt loop instead of 2 belts forming a loop between machines. Okay, if you have watched all the way here, I want to give you a little reward. It's homework of answering these 2 questions. Suppose I'm pumping some water from one tank to the other. Suppose the source tank has A amount of water out of X capacity, while the target has Y capacity and is empty initially. How long does it take for the source to be emptied or for the target to be full? Now the answer is it takes forever. Well, this would be a direct contradiction to what we have observed in Factorio. So you could try to figure out how it really works in Factorio. Okay? Let's suppose in this hypothetical situation, I'd like you to compute what number of ticks it takes for the target to reach a value u that's less than the minimum of y and a. And I can tell you the answer. The answer is x times y over 100 y minus a times ln of a times y minus u over y times a minus u. This is a very simple differential equation problem. And if you solve it, make sure you send it to me. Bye!